Hello everyone, welcome to the channel. I am Ramadevi Gajul and in today's video we are focusing on a key concept in compiler design, that is the target language in code generation. So this is one of the most critical stages in the compiler pipeline and I will walk you through its importance, how it works and what models and optimizations are used. So let's get started. We begin with the final phase of the compiler, that is code generation. At this stage, the intermediate representation, often abbreviated as IR, is translated into actual machine code that a processor can execute. And the goal of the target language in compiler design is to produce efficient, correct code. But to do that, we must understand the target architecture, the instruction set, the register structure, memory model, and more. This makes code generation not just a mechanical translation, but a process where performance and accuracy really matters. So, what exactly is a target language? In compiler design, the target language is usually a low-level language. It could be assembly or even binary machine code that closely resembles the final output the CPU executes. It's the output of the code generation phase and it must balance two things, that is simplicity, so the compiler can generate it easily, and the practicality, so it performs well on real machines. Let's look at a simple target machine model, which is often used in compiler courses to illustrate code generation. So this model typically supports load, that is to move data from memory to register. Second is store, to move data from a register back to the memory. And next is arithmetic operations like addition, subtraction, multiplication, division, etc. And the last one is jump or branch. These instructions manage program control flow. So the architecture follows a three address format using registers like R0, R1, R2 and so on. The simplified model helps us understand the fundamentals of generating code before moving on to more complex real-world architectures. In this model, load and store instructions are central to moving data in and out of the memory. Let me show you how a load instruction like load R1 x to R1 is equals to m of x. So it loads the value at memory address x into register R1. So effectively R1 is equals to m of x. A store instruction like st x comma R1 to the m of x is equals to R1 means store the value in register R1 back into the memory location x, or m of x is equals to R1. So these instructions define the data flow between the memory and the processor. Next we have computation or arithmetic instructions. These usually follow the format OPDST, SRC1 source to for most operations. So OP is the operation like add or sub. DST is the destination register, and SRC1 and SRC2 are the source operands. For example, add R1, R2, R3. This translates to R1 is equals to R2 plus R3. Here a key point to note is all operations use registers only. Memory is not used directly during arithmetic. This is consistent with most real-world architectures which favor register-based computations for speed. Let's move on to jumps and branches. Jumps and branches. These instructions control the flow of execution in a program. So first, an unconditional jump. An unconditional jump like BRL simply moves the control to the label L. Next is a conditional jump. These conditional branches allow for decision making. For instance, BEQZ R1, L means if R1 equals 0, then jumps to label 1. Then jumps to label 1. Next is control flow. It is essential for implementing if statements and loops. So these are the building blocks for control structures like if statements, loops, and switch cases in high-level languages. Next, addressing modes. So one of the powerful features in code generation is the addressing mode, which determines how the location of data is interpreted. Here are the 4 common types. First is direct. Here the variable name refers directly to the memory location, for example X. Second is indexed. It typically used for arrays where the final address is computed as base plus index, for example A of R. Next is indirect. Here a register contains the address of the data such as R or 100 of R. And last one is immediate, uh, where the operand is a constant value like 100. Choosing the right addressing mode can impact the efficiency of code. Finally, let's look at the instruction cost model. So it is used to estimate how expensive different operations are in terms of performance. First is register operations. Register operations are the cheapest and have a cost of 0 since no memory is involved. Next is memory read. Like load R1, X have a cost of 1 due to a memory access. And next is indirect read, which involve dereferencing the pointers, are more costly, about 2 units. The ultimate goal in code generation is to minimize this cost, especially memory operations, as memory is much slower than registers. So to conclude, the code generation is the final and critical phase of compilation. The target language is what the compiler produces, usually a low level efficient representation of your program. So we explored a simple machine model, key instruction types, and how to optimize for performance using cost models. Understanding this phase helps us appreciate how high level code gets transformed into efficient executable instructions. Thanks for watching.